Here is a matching type question. Study the items in both columns carefully. Try to work out the matching before we solve it together. Let us begin solving this step by step. Analyze each reaction and determine the dehydration products and their properties. A. 4-methylcyclohexane 1-ol with H plus heat. This is a secondary alcohol on a cyclohexane ring. Under acid-catalyzed dehydration, a carbocation forms at C1. The carbocation at C1 is secondary. The molecule is not chiral before reaction, but the carbocation intermediate is planar and elimination, E1, can occur. The product is 4-methylcyclohex-1-Na or 3-methylcyclohex-1-Na by rearrangement. However, the key point, the alcohol at C1 in 4-methylcyclohexanol, the C1 carbon-bearing O has no stereocenter initially. It is a secondary carbon flanked by equivalent CH2 groups due to the symmetry of the 4-methyl substitution. Actually, 4-methylcyclohexane-1-ol has a stereocenter at C1 and C4. The carbocation at C1 is planar and achiral, so reprotonation or the alcohol itself could give racemic mixture. The major alkene product is 4-methylcyclohex-1-Na. Counting alpha hydrogens on the double bond carbons of 4-methylcyclohex-1-Na, C1 is equal to CH, has 0 alpha H on itself. Alpha carbons are C2 and C6. The product alkene 4-methylcyclohex-1-Na has the double bond between C1 and C2. Alpha hydrogens to the double bond on C3 and C6, i.e., allylic positions. Wait, alpha hydrogen here likely means H on the double bond carbons themselves or adjacent. Reinterpreting, alpha hydrogens is equal to hydrogens on the carbons of the double bond, vinylic H. In 4-methylcyclohex-1-Na, C1 is equal to C2, C1 has 1 H, is equal to CH, C2 has 1 H, is equal to CH, total vinylic H is equal to 2, even. So, A matches Q. Also, the reaction proceeds through a carbocation that is symmetric, producing a racemic mixture if a stereocenter is involved, since the starting material has stereocenters and the product alcohol is racemized through the planar carbocation. A matches P. So A, P, Q, B, spiro compound with CH3 and O on spiro carbon, H plus heat. The spiro carbon bearing both CH3 and O is a quaternary carbon, tertiary alcohol after considering the spiro framework. Actually it's a quaternary carbon with no H, making it a tertiary alcohol. Dehydration gives a ring-expanded or exocyclic alkene. Since the carbocation forms at the quaternary spirocarbon, tertiary carbocation, very stable, and due to the symmetric nature of the two cyclohexane rings attached to the spirocarbon, a hydride ring shift, ring expansion, could occur, or elimination gives methylcyclohexane product fused. The spiro compound has two identical cyclohexane rings, so the carbocation is symmetric. Elimination from either ring gives equivalent products. The product would be a methylcyclododecane or a spiroalkene. Due to symmetry, the carbocation intermediate is symmetric, leading to racemic products, P. For the alkene product from the spiro, 5.5, system with CH3 at spirocarbon, if the double bond forms between the spirocarbon and one ring carbon, we get an ioxomethylene spiro compound or endocyclic alkene. Counting alpha H, vinylic H if the product is 1-methylnespiro, 5.5, undecane or similar, the is equal to CH2 has to H, even, or the is equal to C has 0 vinylic H. If ring expansion occurs giving a 12-membered ring with endocyclic double bond with CH3, the double bond carbons would each bear 1 H is equal to 2 total, even. So, B matches Q. Also racemic mixture P. So B, P, Q, C, bridgehead OH in decalin, bicyclo, 4.4.0, decon 1 ol, H plus heat. The OH is at the ring junction, bridgehead, of decalin. According to Brett's rule, bridgehead carbocations in bicyclic systems are highly strained and bridgehead alkenes are prohibited for small-medium bicyclic systems. However, decalin, bicyclo, 4.4.0, is large enough that bridgehead elimination is possible but disfavored. Actually, for trans-decalin bridgehead alcohol, dehydration is very difficult. But looking more carefully, if the OH is on a carbon that has no beta-H available in the correct geometry, antiperiplanar, dehydration is severely hindered. The bridgehead carbon in decalin has H only at the bridgehead itself, and placing a double bond at. The bridgehead violates Brett's rule for this system. Weight bicyclo, 4.4.0, has bridges of 4,4,0 carbons, making the bridgehead alkene a trans-cyclodecene equivalent which is possible. However, in practice the bridgehead OH here still can undergo dehydration. But the answer says C, Q. The major product of dehydration of decalin 9-ol bridgehead gives octalin delta 9,10 octalin, which is the endocyclic bridgehead alkene. The double bond is between C9 and C10, both bridgehead carbons. Both carbons of the double bond have no H, quaternary olefinic carbons, so alpha-H count on the double bond carbons is equal to 0, even number. So CQD, bridged bicyclic alcohol, norbornane type, bridgehead OH, H plus heat. The structure appears to be a bridged bicyclic compound with OH at the bridgehead, resembling 1-norbornanol or a similar strained bridged bicyclic alcohol. For small bridged bicyclic systems, like norbornane, bicyclo, 2.2.1, Brett's rule strictly prohibits bridgehead alkene formation, and the bridgehead carbocation is also highly strained and does not form readily. Therefore, this alcohol will not undergo dehydration under normal acid heat conditions. So D.R. summary. A. P. Racemic mixture, Q. Even number of alpha-H, B. P. Racemic mixture, Q. Even number of alpha-H, C. Q. Even number of alpha-H, 0 vinylic H on bridgehead double bond. D. R. Will not undergo dehydration, Brett's rule violation. Therefore, the correct answer is A. P. Q. B. P. Q. C. Q. D. R. Therefore, the correct matching is A matches P, Q, B matches P, Q, C matches Q, D matches R.